Today's discussion is going to be covering Chapter 3, which is going to be, what you look at your book, it talks about cellular environment, fluids and electrolytes, and acids and bases. What I will try to do is to try to correlate it to what anesthetically what we do, okay, and to start giving you some attachment point where you can begin to sort of apply this in clinical situations. First of all, let's talk about something very simple, which we consider water, but it's not such a simple molecule. It's actually pretty critical for life. 60% of your total body content is actually water. And water is, of course, a universal solvent. It has a neutral pH of around 7, and it forms very strong covalent bonds, which means that it is able to keep things in solution. The other thing that's very helpful about having water in our life is that it boils at a very high temperature. If we had alcohol in our bloodstream, on the other hand, it would boil off very fast, and it wouldn't be something that you'd be very conducive to survival. It also freezes at very low temperature, 0 degrees Celsius or 30 degrees Fahrenheit, okay? And has a lower density. It has high specific heat, and it has a nice high surface tension. The nice thing about having water is that having high surface tension, it means that it forms into bubbles, okay, or it forms into like a sphere if you were to put it in space, where it has zero gravity. Okay? If you put water onto a table, it will immediately form into like a spheroid kind of shape, and the same thing happens inside your body. You can actually tell how much water content is in a human being just by looking at their face a lot of times. Okay? If you see somebody who's significantly dehydrated, they will appear to you, if you have clinical acumen, that the person they have very sharp borders on their face. Everything looks very cut and chiseled. Versus somebody who has a tremendous amount of high water content will look more rounder in shape. Clinically, we see this in children. Children have a much higher percentage body water in comparison to adults. And as you look at a kid's face, it appears to be round, and it's simply from these increased water content. As you get older, which means you see the person who's aged in the 70s or 80s, they're actually functionally dehydrated. And as you can see this by their face, that it's more chiseled, it's more sharp in image, and that's because there's less water content in that individual. The importance of understanding that is that it is kind of important for when we put people under anesthesia. Any agent that we use to put somebody under in the induction phase, which means that we put them from a wake state into an asleep state, most of our agents that we use for that are vasodilators. Specifically, they're more venodilators. So as a consequence, you drop the preload in the heart, and you will see a drop in blood pressure as a consequence. We're essentially a big bag of water, which we contain not only water, but we also contain other essential molecules such as electrolytes. Okay? We talked about this about 2 weeks ago, talking about size-wise. Salts are the size of peas. Okay, so those are small molecules. Sugars are a little bit bigger, followed by amino acids, which eventually make up the essential proteins, fats, and vitamins, rare metals, and eventually, if you're looking at the blood, you're looking at red blood cells itself. Now, be very careful as we go on to this discussion to make sure that you understand where you're looking at the water content. Most of the time when we are drawing blood tests, we're only looking at the intravascular compartment. Okay? We're not really looking at the intracellular environment. Okay? And that's significantly important because when you start applying some things that we use clinically to make some situations better, such as hyperkalemia, you have to understand the cellular environment as well. And I'll try to differentiate those two compartments as we go along. Now, the body compartments that we're going to think about next is that we have one major compartment, which of course is your whole total body, which is the actual compartment containing water is approximately 55 to 60% of your total weight. That is broken down into 3 major compartments. Okay? The 2 major components are the extracellular compartment, and the other one's the intracellular compartment. By far, the most important of these is the intracellular fluid compartment. Okay? That means your brain cells, all the organ cells that you have in your body, those compartments have to be maintained at a very regimented fashion with a very strict pH for survival. Okay? You go out of a certain pH range or you change the nutritional status of the intracellular environment, the cell will eventually die. Okay? And actually dies very quickly. So the body is really trying to keep that compartment at all costs to be very stable. To do that, or how to provide the nutrients, the oxygen, to those individual intracellular cells is by using the compartment, which is the extracellular fluid compartment. The delivery of oxygen and nutrients is via the extracellular compartment, via the intravascular compartment, which accounts for only a very small percentage, which is only about 6% of your total body weight. So there's really not a lot of blood in your body, okay, in comparison to the total fluid volume. Okay. There's only approximately 3 liters in your bloodstream. So if you're losing 100 cc's per minute in a blood loss, you can be dead pretty quick. If you're losing a liter, you're dead in 3 minutes. Okay? And that can be something you can see in the operating room, believe it or not. Okay? When you see an aortic tear or aortic dissection, most people are dead within about 45 to 50 seconds. Okay? And so it can be pretty quick. Okay? The interstitial compartment is very critical when you're talking about everything beyond the brain. Okay? All the compartments from your head down, okay, contain interstitial space. Okay? The interstitial space is where fluid acts like a buffer, okay, between the intravascular compartment and the intracellular compartment. Okay? The interstitial space can be drained either back to the capillaries, the bloodstream, or it can be removed and cleaned out by the lymphatics. What's important about you to understand, maybe not so much just yet, but you will understand over time, is that this interstitial compartment does not exist in the brain. Okay? The brain is a completely different mechanism of how it actually controls what comes in and how it buffers it. And it does that by the effective compartment called the blood-brain barrier. Okay? So the blood-brain barrier actually separates the brain and keeps it very, very safe in comparison to all the other organ systems in the body. Anyways, the interstitial fluid accounts for about 15 to 16% of the total body weight, which accounts for about 11 liters. Now, that fluid that's inside this interstitial space will be lymphatic eventually. It can form synovial fluid. It can form biliary, hepatic, pancreatic, CSF, a lot of different things that it can end up forming. Okay? Here's how I want you to think about this. Okay? You can think about this as 3 different compartments, okay, which being the most furthest away from the actual bloodstream is the actual intracellular compartment. The intracellular compartment has this interstitial space between it and the blood vessel, and essentially it protects the intracellular compartment from changing too rapidly. This interstitial compartment basically is acting as a buffering system. It's protecting the cells from rapidly changing due to changes in pH or changes in nutritional status that are occurring into the intravascular space. Now, the intracellular space is very, very different than these 2 compartments. These are the extracellular compartments. The intracellular compartment is very high in protein concentration, okay? And it has selectively much higher potassium than the extracellular compartments. Okay? The major electrolyte inside your cells is actually potassium for a cation. On the other hand, the extracellular compartment, the major electrolyte in there is actually sodium. Okay? Now, why would that be the case? Okay? Simply because it begins to be important when you talk about electrical gradients. Okay? If you want to have electricity, you want to have one compartment to be containing one set of electrolytes in comparison to the other one. And the way the arrangement is set up is that the intracellular compartment is actually very low in sodium in comparison to the other compartments. Now, when you look at the extracellular compartment, it's broken down into 2 components, interstitial and the intravascular. The intravascular has some specialized cells in it, which allow for the transfer of oxygen and CO2, which of course are the red blood cells, which carry the hemoglobin. So the interstitial compartment does not have normally, under most circumstances, red blood cells in it. Okay? What it does have in it, depending on which compartment you're looking at, if it's lung or it's other forms of tissue, it actually has a much lower protein content that's normally found inside the intravascular compartment. Okay? And this becomes more evident when we start talking about Starling's law and stuff. Okay? But just to understand this sort of arrangement. The other way you can look at this as another example is by looking at it this way. Imagine that it's a box, and that's 7%. A doubling of that would be 14%, right? Which is, in this case, the interstitial compartment, which ends up being around 16%, which is almost an essentially doubling effect. And the next one, you would see another doubling, right? It should be around 32, but in this instance, it's 35%. Now, the reason that this is important for you to understand is when we give fluids to a patient, okay, it eventually equilibrates all the way down to the cellular level. Okay, so if I give you a liter of crystalloid, okay, eventually it will redistribute to all the compartments. But the compartments that it redistributes very rapidly into is in the extracellular compartments. So essentially, it moves into these three boxes. Okay? Now, I don't know how many of you have heard this, but normally people are taught that if you lose 1 cc of blood, how much crystalloid do you give? 3 cc's. Okay, so that's, and the question is, most students should have is, why? And if you're not asking those kind of questions, then this is the time to start asking them. Okay? You should start asking about everything as to why we do what we do. The reason we give 3 cc's is that within 45 minutes of us giving a liter, those 3 boxes are going to get equivalently infused with the same amount of fluid. So if I give a liter, okay, I'm going to put in basically 333 cc's in this compartment, which is only 333 cc's stays intravascular, and the other 666 cc's are going to be in interstitial space. Okay? You've all seen this in the ICU when you gave a lot of fluids to a patient and you're wondering, where is all this fluid going? Okay, it's not saying intravascular. There's some situations where the person's vascular system is leaking even faster than normal, and this equilibration is taking place very rapidly, which we call third spacing. So what they're talking about when they're talking about third spacing, they're really talking about the fluid shifting into this compartment too rapidly. Now, some of the books will tell you that say, well, you know, if I give somebody 10 liters, that won't really have that bad of an effect. But just think of that. Okay, if I give 10 liters to somebody, only 3.3 liters is going to stay intravascular, and the other 7.3 liters is going to go into the interstitial space. Okay? What's that going to do with the actual distance between the intravascular to the interstitial space? It's going to increase it. Obviously, it makes sense. Okay? And as a consequence to that, it means that it takes longer for the oxygen to travel from the intravascular compartment all the way to the interstitial space. And then functionally, you're going to develop some degree of metabolic acidosis in that patient. Yes? No, interstitial. The actual, when you get the equilibration taking place, it equilibrates into the interstitial space first. Okay, that compartment is able to hold a tremendous amount of volume in it, okay, and is able to expand. That's what eventually induces what we call edema. Okay? The cells eventually do accept the volume, but they really try to refuse it as much as they can. Because if you give too much volume to the cell begins to dilute out and it starts causing big problems for the cell. So the cell, if it's got an active sodium-potassium ATP pump and can still do its work, it'll try to keep the water out. Okay, so it keeps it into the interstitial space. All this stuff is pretty critical for you to understand, so don't give a, you don't pour in fluids into people and expect their outcomes to be great. There is going to be bad outcomes, and there's a consequence to this. The outcome that's going to be bad is that you'll see in the intensive care unit the next 2 days is a certain degree of metabolic acidosis. And you sort of search for it and say, why is this person acidotic? And it's simply because the cells are having a stressful time getting that oxygen across. You can somewhat make up for it by increasing your FiO2s and your PaO2 values, but you can only do so much. So just understand that don't flood people. Try to not to do that. Yes? That's right. The compartment literally gets physically bigger. The volume displaced into it basically increases the space, which is what you see clinically as edema. We've all seen patients that come out with 10 liters of fluid. Their face is round. Their eyes are completely closed because they have so much edema. Okay? Their airways edematous. Their tissues edematous. When you touch them, they feel like dough. That's all bad signs that you've given too much fluid to somebody. Okay? Now, sometimes you're forced to doing that because you have no choice. Okay? But I'm telling you, if you're doing that because you're losing blood loss, that's not appropriate. If you're losing that much blood, what should you be giving the patient? Blood. Give the patient blood. And now the studies are demonstrating that it's not good to give these people high amounts of volume like this. We're actually seeing higher mortality rates when we do this. So now finally some of the data is catching up with some of the basic science. Okay, so you can look at your compartments here and how they're separated. The actual intravascular compartment is separated between that compartment by simply a plasma membrane. Okay? And just like any other plasma membrane, it has the capability of using pumps, sodium-potassium pumps, to exchange fluid. Okay? And the other thing that's helpful to understand about this is that the interstitial space, which is here, can be drained back in either by going fluid backwards this way, or it goes via lymphatics back into the plasma. The cellular space here, okay, is pretty much a very highly protected environment that is really just wanting to keep itself nice and stable without really making any major changes at all times. Okay. But the importance of this is to make sure you remember that the plasma, the intravascular compartment, is basically the highway where all the nutrients travel. If you affect any way the intravascular compartment, either you impede the flow through that area, you impede the delivery by impeding the cardiac output, then you eventually cause the cells to die because they're not getting any oxygen or nutrients to them. Okay? Now, is oxygen a nutrient? It's not. It's not a nutrient. Okay? Make sure you understand the difference. Oxygen is an electron acceptor. Okay? It's not considered a nutrient. Okay? Oxygen by itself cannot convert and form energy out of it. Okay? Oxygen basically uses its electron accepting capability to allow for the pathway of fuel sources to finally break stuff down. Okay? So without oxygen, you can't break down basically amino acids, proteins, and carbohydrates to their full extent. Okay? But if you don't get enough nutrition, you still are very, very dead, even though you got plenty of oxygen. Just think of that. You're walking around, right? And what are you trying to achieve every day? You eat breakfast, lunch, and dinner. Are you getting plenty of oxygen? Yeah, but if you stop eating breakfast, lunch, and dinner, you're still getting plenty of oxygen. You're still end up being very dead. Okay, so nutritional, what actually provides you the fuel source, are only three things: carbohydrates, proteins, which are amino acids, and fats. Those are your only your nutritional sources. Okay, vitamins are considered essential vitamins, or essential a part of the nutrients, but they're really not really important in the sense of energy production. Okay? Somebody asked me that the other day. I just wanted to make sure people understood the difference. Body content, okay, of water varies between age. Okay, if you look at a younger person, like a baby, their water content is actually very high in comparison to an adult. As you get older, the water content actually reduces. Also, water content depends on gender. Patients with different body habitus will actually contain different quantities of water. If the person has a high lipid content, they have a lot less water, okay, versus the person who's very muscular has actually very high amounts of water. And to test this, you can actually drop somebody in a pool. Okay? And then if you're an athlete, you want to sink. Okay? If you get in the water and you sink to the bottom really quick, that means that you're almost all made of muscle. Versus if you have a high lipid content, you'll float. Okay? So that's why seals have a lot of lipid content. It helps them keep them afloat in the ocean. Versus something that would be purely muscular would end up being requiring high velocity to keep going. And that's what a shark does. A shark has to constantly swim because he can't literally float. Okay? It has some air blast in place, but it's a different kind of system. The body water weight in infants is around 80%. In adults, you're looking at the males account for about 55%, and females tend to have a higher body fat content under most conditions, and they account for about 45% of their total body weight. Okay? And obese people have even less water. Sorry this didn't come out in my slides too well, but I think it comes out okay on your slides. If it doesn't, then let's concentrate on some of the essentials. Okay? What this basically shows you is the different concentrations of electrolytes in different compartments. If you look at the two major things that I want you to separate out, let's draw a line right here. This is your intracellular, and these two are your extracellular space. Okay? What I want you to understand first is that the sodium concentrations in the extracellular space are very high. Okay? So when we talk about later on about electrical charge, this is a compartment we're talking about that has high sodium content. Okay? So the normal sodium in plasma is like 140 milliequivalents per liter. In the interstitial space is almost the same. Okay? Potassium, so sodium in the extracellular space, which we measure, is really around 140. Potassium normally in the interstitial as well as in the plasma space is 4. Okay? The other one that's important is the calcium is around 1.3. Okay, and that's the ionized fraction. And then magnesium is at 0.8, and chloride's 108. So that's really where you have to sort of draw the line as the ones that I really want you to memorize. And the bicarb or carbonic, the bicarb component is 24 to 28. Okay, that's the interstitial, the extracellular compartment. Okay, you have to know that concentration for the test. Okay. As for the intracellular compartment, what I want you to specifically pay attention to is that the intracellular sodium concentration is actually very low. It's around 14 milliosmoles per liter. The potassium, on the other hand, is very, very high at 140. Okay? So why does that happen? Because the cells have sodium-potassium ATP pumps in them, and they basically push out the sodium out of the cell and pull in potassium into the cell. Okay. The other thing that's very, very low and actually zero inside a cell is what? Calcium. So why is that the case? Right, it's stored inside specialized vacuoles. If you're looking at skeletal muscle, it would be the sarcoplasmic reticulum. Free ionized calcium is extremely dangerous. Okay? It'll denature DNA, it'll affect proteins, so it's something that you don't want floating around the cytosol very much. So as a consequence, the cell very highly regulates calcium inside the cytosol. Okay? Magnesium, on the other hand, has a very high concentration inside the cell. Okay? which accounts for about 20 milliosmoles per liter. I tend not to ask that too much, so don't worry about that too much. The other thing that you see is that the chloride level is just very low. That doesn't make sense, right? You have a high potassium of 140 milliequivalents, but you don't see any really negative anion. Where is the anions? Notice what's negatively charged inside the cell? No, potassium is positively charged. Potassium is a charge of +1. There you go, proteins. Proteins are in very high concentrations inside the cell, which is why you don't need a bunch of chloride inside the cell. When you look at down here at the protein content inside the cell, it's actually very high, 4 milliosmoles per liter, which accounts for a lot of the negative charge that you're seeing. Okay. The protein content in the interstitial space in comparison to the intravascular space is very low. Okay, and the reason that is because the interstitial space is constantly being cleaned out by the lymphatics, as well as the cells really are trying to take up all protein, so that it really leaves the interstitial environment pretty much barren of protein under normal circumstances. The only exception to that is the lung. Okay, the lung tissue actually has around 50% protein content that's found inside the intravascular compartment. So it's actually a very loose capillary network when you're talking about the lung. Okay. All right, go on from there. Now, one of the things that you have to understand about is that molecules do move in and out of the cells via certain different ways. Okay? The major one of importance in discussion is diffusion. Okay? And diffusion tends to be a passive process. It usually goes down a gradient, okay? So it's dependent on several factors. It's dependent on the molecular size of the compound. The bigger the molecule, what do you think the chances of it going across? The less. Okay? So the smaller the molecule, the more readily it comes across. The more molecular charge it has, the less likely it is to cross. Okay? If it's negatively charged, it has less likely chance than a positively charged molecule. Okay? The other thing that's important for molecules is because you are going through a lipid bilayer, that if it's fat soluble, then it's more likely to cross through the cell. The importance of understanding that is that most of our anesthetics are lipid soluble, so as a consequence, they go into the membranes rather easily. Okay? And diffusion is also dependent to a certain degree on the permeability of water. The next thing we'll talk about subsequently will be on Starling's law, which also applies hydrostatic pressure into this equation, understanding that a certain amount of hydrostatic pressure is critical for fluid from shifting from the intravascular space into the interstitial space. What actually keeps fluid in the intravascular space is the high protein concentration that's in it, okay, as well as the red blood cells, or it helps because they have a high protein content. That is what we count for what's called oncotic pressure. Oncotic pressure basically tries to pull water back out of the interstitial space into the intravascular space. You can get into certain disease states where, let's say somebody has kwashiorkor, which is severe protein malnutrition. That person will develop significant edema because they won't pull back the fluid out of the interstitial space because they don't have enough protein in their bloodstream. Okay? Then you have a discussion on osmotic gradients, and basically that's a discussion about where water goes, and water always goes where the high salt content is at. So let's look at these different mechanisms. First, let's look at the hydrostatic pressure. Hydrostatic pressure basically is equivalent to a filtration. If I put more hydrostatic pressure into something, it means that it begins to exert more energy into the molecules to push them through a membrane. Okay? So if I induce, let's say, somebody to have hypertension, that basically increases their hydrostatic force of the molecules around surrounding blood vessels. As a consequence of that, most patients that are severely hypertensive are actually severely dehydrated. Okay? And that's an important thing to know. Most students, when they see a blood pressure of 170, they go to themselves in their head and say, this patient's going to be easy to put to sleep. As soon as we put them to sleep, the blood pressure will be nice and stable. It'll drop a little bit. It won't be a big deal. Actually, it's a reverse. When you give a vasodilator to somebody who is already volume depleted, they fall apart really fast. So somebody with significant, very out-of-control hypertension, they're actually miserable to put to sleep. Okay? It's very difficult to keep their blood pressure stable in the process. Okay? The osmotic pressure is the next mechanism, which has to do with where water content's going. Water always follows sodium content. So let's say you take a person and make them eat huge potato chips and beer. So they're at a Super Bowl party and they eat a bunch of potato chips. Okay? That has a tremendous high sodium content. And as a consequence to that, once the sodium gets into the bloodstream, which it does after it goes into the GI tract, that sodium acts as a what? It begins to pull water out of the interstitial space. So the intravascular space rapidly increases. Okay? And if you have somebody with a heart problem where they can't really pump very effectively, their preload goes up very rapidly and the person goes into congestive heart failure. So very commonly after Super Bowl parties or any of these major events where you see a lot of people eating a lot of potato chips and a lot of hot dogs, or anything that has a high sodium content, people come in with congestive heart failure. Okay? As for diffusion, that has to do with, basically what we talked about previously about molecular size, and also depending on number of molecules that you have available. And when we talk about later on about anesthetic agents, we'll talk about how diffusion takes a very big important part and how the volatile anesthetics travel from one compartment to the next. Now, Starling's hypothesis, which is very different than Starling's law, which we talk about later on in cardiac, has to do with how fluids or how material moves via what's called net filtration through blood vessels into the interstitial compartment. You have basically two forces that you have to deal with, which is what are the forces that actually favor filtration, which means how much the fluid transfers from the intravascular compartment to the interstitial space. Those forces favoring filtration are hydrostatic pressure and oncotic pressure in the interstitial side. Now, most of the time, the oncotic pressure in the interstitial side is actually very low, so it's very not significant under most conditions. There would be certain disease states where you do get that a very high concentration of oncotic load, such as somebody who has lymphedema, okay, where the lymphatics don't really work properly, and as a consequence, protein content begins to increase in the interstitial space, which then acts to pull more water into the compartment, causing edema to form. But under most circumstances, that's usually not significant. The forces that oppose filtration, on the other hand, which tend to be very low, is the actual interstitial pressure, or hydrostatic pressure, which is normally low, and the oncotic pressure on the blood side of it. So when you look at this equation, actually I have the next further on, okay? So that's what I was just talking about. So when you look at the equation, you're basically using the following picture to sort of explain this. Let's go into the different components. One, the fluid is coming in through here and the hydrostatic pressure begins to push the fluid out. Okay? So that's a force favoring fluid to shift from the intravascular space into the interstitial space. Okay? The force that's opposing that is the hydrostatic pressure that's inside the interstitial space. And that normally is very low. So it really effectively doesn't do a very good job. The indications where that would be reversed would be a situation where you take and put a stockinette on a patient. Okay? When you put a stockinette on a patient, what you're literally doing is you're increasing the hydrostatic pressure in the interstitial space. And that helps prevent fluid from leaving the intravascular compartment. Okay? The other thing that you can do to increase hydrostatic pressure is if the lymphatics were to become obstructed and then the interstitial fluid begins to accumulate, then the pressure begins to rise, and that also helps prevent worsening edema. The person's still going to get edematous, but it's going to hopefully slow it down a little bit. The oncotic pressure normally is very, very low inside the interstitial space, so it doesn't really help pull the fluid into the interstitial space. It's mostly, almost all the time, due to hydrostatic forces. As for, you can see here, the oncotic pressure is actually pulling back significant amounts of the fluid back because of the protein content inside the intravascular compartment. And that's what you sort of have to understand. Which ones are helping and which ones are opposing this action. Now, what you'll talk about here, this is the osmotic equilibrium. Okay, we sort of talked about this last week. Somebody asked me if sodium saline, normal saline, was considered hyperosmotic. Depending on which book you read, most of us will consider normal saline as hyperosmotic in clinical. Okay. Some of the books will actually say that it's isoosmotic, but it's really not. The reason it's really not is because the sodium concentration is actually higher than what you're actually delivering. Okay, the sodium content of what you're delivering is higher than what's inside the intravascular space. Remember, the sodium content in the intravascular space is what? 140 milliequivalents. Okay, if I give you normal saline, the actual amount of sodium inside normal saline is 154 milliequivalents per liter. Okay, so that means that the salt content is actually high in that fluid. And so what happens to the interstitial space? Water leaves the interstitial space to dilute this out to eventually go back to 140 to 142, let's say. And so it is acting as an interstitial dehydrator. Okay, it is going to pull water out of the interstitial space. Now, how long does it last? Not very long, because eventually you get equilibration, which takes about 45 minutes. Now, if you're looking at how we actually do some things in military, is that they sometimes use what's called hypertonic solutions. Okay, and hypertonic solutions can be as much as 300 milliequivalents of sodium inside that solution, okay, or more higher. So these are very dangerous solutions if you give them too fast, because essentially what happens is you pull all the water out of the interstitial space, and then the cells then begin to starve for fluid. Okay, so that's not what you want to do. The reason these are used is because if you have a medic who's running around in the field, it's hard for him to carry 10 liters of lactated ringers. Instead, he can carry 10 50 cc syringes very easily with low weight, and that can actually keep 10 men alive very easily. Okay? They've actually had some reported cases of some people having to have extended travel times where you just take one of these syringes and you give 1 cc every 15 minutes. And that is enough to carry that person through by keeping the fluid intravascular. Okay. Will that person be a little bit dehydrated intracellular? The answer is yes, but as long as you go slowly, it doesn't seem to have any severe deleterious effects in the cells. Okay. But you got to be careful. If you give 50 cc push of it, that person will be dead in front of you. Okay. You would basically pull all the water out of the red blood cells, and that would not be a good thing. Okay. On the other hand, what actually will kill you very, very fast is if you give somebody free water. If you inject free water into your bloodstream, what will happen to your red blood cells? They'll burst. And the free water will rapidly travel into where the sodium's at, which is inside the red blood cells, and the red blood cells will enlarge and eventually burst. So that's one thing you cannot do. You cannot apply free water directly to any kind of organ as well, because it's not good for that cell. Now, free water was used in the past, and still is, for one thing. What do we think it's being used for? Debridement. It's good for debridement of tissue, which means that you're killing the cells and then you're cleaning it up. So you're taking the surface of the cells that are basically dying, and applying this stuff to sort of clean out the debris. Okay? And that's what this is trying to show you, what happens with when you give a hyperosmotic or a hypoosmotic solution, and how it equilibrates over time. Make sure you go over this and understand it thoroughly so you can get it on the test, because there will be a question on the test on this. Now, what I try to do for you is to try to give you clinical scenarios so it sort of makes it work. The clinical scenarios are the following. I'm not going to give you the answers to it today, just to know these questions for the test. Okay? Things I've already sort of given to you already. So what happens to a patient in intravascular volume in hypertensive patients? 2, what happens when oncotic pressure decreases in intravascular space? What happens when you administer D5W in a patient's IV? I just told you that. What happens when you administer colloid to a patient? What happens when the patient has increased capillary permeability? What happens when a patient has increased capillary permeability and you administer colloid? And then what happens when a patient develops a blood clot in saphenous vein? And then what happens when you eat lots of potato chips? Okay, I just talked to you about that too. Okay, so some of these I've already given you the answers to, but make sure you know these because some of these will actually come out and be test questions. The next component is a discussion of how this fluid is actually redistributed. The biggest issue is the formation eventually of what's called edema. Okay? And edema does not necessarily mean just right-sided heart failure. Okay? Which is when we go talk into cardiovascular physiology, we'll come over and talk about this over and over again that right-sided heart failure does form edema. Okay? But there's other causes of edema as well. And you got to know which of those that you're dealing with. Okay? It's basically edema is a problem of fluid distribution. It does not always indicate excessive intravascular fluid excess, actually. It may actually indicate just the opposite. And it's basically, edema is basically an accumulation of fluid within the interstitial space. Now, what causes edema could be simply the following 5 things. Increases in hydrostatic pressure, so patients that are hypertensive will develop edema. Patients that are losing plasma albumin for some reason from nutrition or lack of production of plasma albumin. It could be also due to weakness in the capillary wall, where the capillary wall develops increasing capillary permeability. And the last one is lymphatic obstruction. Now, for the people that are more visual, the book has this kind of description. I don't really like this graph, so what I did is I made another one for you. Okay? And what I basically did on this graph was to show you the top 4 reasons for the problem, which is hydrostatic pressure, oncotic pressure, capillary permeability, and lymphatic return. Those are the 5 major headings of possible disease processes. If you have hydrostatic pressure, if you see an increase in capillary hydrostatic pressure, you will start forming fluid into the interstitial space, which is what we just talked about, how hypertensive patients will begin to spill their volume from the intravascular into the interstitial space. The second cause, which is oncotic pressure, if you see a decrease in capillary oncotic pressure, usually from lack of nutrition or due to spillage into the interstitial space, like in certain disease processes, and eventually you develop interstitial edema. The other thing that can actually happen as well is if for some reason the interstitial space is not being cleaned out properly, then the interstitial oncotic pressure will begin to increase, which then also increases your interstitial edema. As for your capillary permeability, normally most blood vessels in your body are what's called tight junctions. Okay? And by tight junction, we're basically talking about that the capillaries are touching each other so tightly that they're basically not allowing fluid to cross over very easily. Okay? In certain disease states like sepsis, okay, or autoimmune diseases or anything that attacks these gap junctions, it will lead to an increase in capillary permeability and let fluid to basically translocate across. This leads to a decrease in overall capillary oncotic pressure, which eventually leads to interstitial edema. Okay? The other sometimes you see is if you get capillary permeability gets too high, it begins to spill the albumin directly into the interstitial space, which then acts like an oncotic puller to pull more fluid into the interstitial space, forming interstitial edema. And the last cause is the actual interstitial edema is normally drained out by the lymphatics. So if you get a disease process where lymphatics are obstructed, then you don't get, you develop interstitial edema. Now, water balance. The main organ of water regulation is the kidney. We're not going to talk about it this semester. You're going to be talking about it in next semester. when we talk about pathophysiology. It's not normally, it's usually in the physiology section, but I just run out of time in that section, so instead we'll talk about kidney later on. Okay? What's something you have to understand, though, is begin to understand what's the ADH mechanism of actually how the kidney is regulated. Okay? And water balance is mostly achieved by controlling antidiuretic hormone, and partly antidiuretic hormone is responsible for thirst. Okay? There's many different kinds of thirst regulators, but ADH is one of them. What you have is if you, for some reason, if you have a decreased circulating blood volume, or you have increasing plasma osmolality, okay, the thirst centers in your body will become activated, and you will get an increase in fluid intake, which will hopefully increase your water retention. The other thing that the body tries to do is it tries to tell the kidney, hey, don't waste water, so it begins to release antidiuretic hormone. This is how you remember it, antidiuresis, okay, hormone. Okay, so it's basically telling the kidney, don't urinate anymore. This leads to a decrease in water excretion, and then increases water retention. Hopefully, eventually, you lead to increasing overall circulating fluid volume, and this begins to drive back down the plasma osmolarity, which then shuts down the production of ADH and thirst. Okay? So when you feel thirsty, that's what's happening in your body. Okay? Now, when you look at this more extensive picture here, this is a breakdown of the system of water regulation, okay, in more detail. The first portion is what causes activation versus what does not cause activation. Under normal circumstances, what you get in activation is from increased circulating, there's two portions of the brain that regulate ADH release, okay? One portion will actually activate and release increased ADH levels, and the other portion will actually cause an inhibition to take place. Okay? Things that will actually cause an activation of ADH will be decreasing circulating fluid volume, which we just showed you, or increased plasma osmolarity. These are actually, one's a volume receptor, okay, and the other one's actually a chemoreceptor, which means that there's different kinds of receptors inside the brain, which then give that modulated effect, which then go on to increase the actual antidiuretic hormone release. Okay? As for the other system, which is an inhibitor, things that will basically shut down the system will be things that increasing circulating fluid volume will actually cause the volume receptors to become more receptive, and they basically cause inhibition to take place. So this mechanism that you have is an activator as well as a negative feedback mechanism to shut the system down. The production of antidiuretic hormone is via the posterior pituitary. There's only two hormones that are released by the posterior pituitary, oxytocin and antidiuretic hormone. The way you remember those is those both are considered emergency hormones that are being released. And oxytocin is basically to keep the woman alive when she has a baby. It's released in high concentrations to cause uterine contraction, so hopefully stop the hemorrhaging. The other thing that oxytocin is very important for, besides contraction, is it's also a part of, I'll talk about that later, don't worry about that. The other important issue about this is the release of antidiuretic hormone in high concentrations. Okay? If you release normally under very high concentration of ADH, it's what's a drug called if you give it in very high concentrations? Vasopressin. Okay, so vasopressin is a direct circulating vasoconstrictor, but it's only in very, very high levels. Under normal circumstances, ADH at low levels doesn't cause that. Instead, it just tells the kidney to hold water by not letting it to diurese. Okay? So under normal circumstances, really vasopressin has a very limited effect on blood pressure. It has it's one of the arms of doing it, but it's very limited. What it does eventually is when it gets released into the bloodstream, it goes to the renal tubular cells to increases the permeability and basically reabsorbs more water. and this causes decreased water excretion. Eventually, this causes an increase in water retention, and that's what keeps the person from hopefully dying from losing volume. Thirst perception is activated when there's less than 2% of water loss or increased osmolality. Okay, so it doesn't take much to make the change. Okay, these osmolality receptors are actually found in the hypothalamus, and they're activated by hyperosmolar changes or plasma volume depletion. As for your ADH secretions, they're activated by baroreceptors, okay, as well as by increased plasma osmolality, and there's also volume receptors. So there's three mechanisms that actually lead to ADH secretion and activation. Okay. The baroreceptors sense decreases in blood pressure by sensing less stretch, and they're located in the carotid bodies in the aorta. And we'll go into more detail later on in endocrine. As for increased plasma osmolality, it's a swelling of the osmoreceptors, which actually decreases the release of antidiuretic hormone. The one that you really have to clearly understand is that ADH is produced by and secreted by the posterior pituitary. Then we'll stop here and go on in 10 minutes.